Number 61 is another finding from Trail of Bits audit of 0x protocol, where it was another high severity finding, again related to specification, in which neither the 0x specification nor documentation stated clearly enough how fillable orders were determined. The recommendation was to define a proper procedure to determine if an order was fillable and detail it in the protocol specification, and if necessary, warn the users about potential constraints on orders. This is related to the broad aspects of system specification of number 136, tests of number 155, and clarity issues of 188 we discussed in the security pitfalls and best practices 201 module. Number 62 is another finding from Trail of Bits audit of 0x protocol, where it was a medium severity finding related to timing, in which market makers had a reduced cost for performing front-running attacks. For context, market makers received a portion of the protocol fee for each order filled, and the protocol fee was based on the transaction gas price, which meant that market makers could specify a higher gas price for a reduced overall transaction rate using the refund they would receive upon disbursement of protocol fee pools. The recommendation in the short term was to properly document that issue to make sure users were aware of that risk, and in the long term, consider using an alternative fee that did not depend on the transaction gas price to avoid reducing the cost of performing front-running attacks. This is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module, and broader aspects of timing in 177, gas in 182, and incentives in 187 from Security Pitfalls and Best Practices 201 module. Number 63 is another finding from Trail of Bits audit of 0x protocol, where it was a medium severity finding, again related to timing, in which if a validator was compromised, a race condition in the signature validator approval logic became exploitable. The set signature validator approval function allowed users to delegate the signature validation to a contract, but if the validator was compromised, a race condition in this function could allow an attacker to validate any number of malicious transactions. The recommendation was in the short term to document this behavior to make sure users were aware of the inherent risks of using validators in the case of a compromise, and in the long term to consider monitoring the blockchain for signature validator approval events to catch such front-running attacks. This is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module, and broader aspects of timing in 177, external interactions in 180, and trust issues in number 181 from Security Pitfalls and Best Practices 201 module. The principle of compromise recording from number 201 of Security Pitfalls and Best Practices 201 module is also relevant here. Number 64 is another finding from Trail of Bits audit of 0x protocol, where it was a medium severity finding related to denial of service, in which batch processing of transaction execution and order matching may lead to exchange griefing. For context, batch processing of transaction execution and order matching would iteratively process every transaction and order, but if one transaction or order failed because of insufficient allowance, the entire batch would revert and need to be resubmitted after removing the reverting transaction. The recommendation was to implement no-throw variants, that is, that do not revert, for such batch processing, and take into consideration the effect of malicious inputs when implementing functions that perform a batch of operations. We've discussed concerns with calls within loops, which is representative of batch transactions, leading to denial of service in number 43 of Security Pitfalls and Best Practices 101 module, and more broadly, the issues of error reporting in 175, and denial of service in 176 of Security Pitfalls and Best Practices 201 module. Number 65 is another finding from TrailorBit's audit of 0x protocol, where it was a medium severity finding related to data validation, in which zero fee orders were possible if a user performed transactions with a zero gas price. The recommendation was to select a reasonable minimum value for the protocol fee for each order or transaction, and also to consider not depending on the gas price for the computation of protocol fees, which would also avoid giving miners an economic advantage in this protocol. This is related to the broad aspects of data validation issues in 169, gas in 182, and incentives in 187 of Security Pitfalls and Best Practices 201 module. Number 66 is another finding from TrailorBit's audit of 0x protocol, where it was a medium severity finding related to data validation, in which calls to set params may set invalid values and produce unexpected behavior in the staking contracts. Set params allow the owner of the staking contracts to reparameterize critical parameters. However, reparameterization lacked sanity threshold or limit checks on all the parameters. The recommendation was to add proper validation checks on all parameters in set params, and where the validation procedure was unclear or too complex to implement on-chain, document potential issues that could produce invalid values. This is related to system documentation in 137, function parameter validation in 138, function invocation arguments in 146, and broader aspect of data validation issues in 169 we discussed in Security Pitfalls and Best Practices 201. Number 67 is a finding from Sigma Prime's audit of synthetics ether collateral, where it was a high severity finding related to data validation, in which there was improper enforcement of supply cap limitation. The open loan function only enforced that the supply cap was not reached before the loan was opened, without considering the loan amount being opened. As a result, any account could create a loan that exceeded the maximum amount of SETH that could be issued by the ether collateral contract. The recommendation was to add a required statement in the open loan function to prevent the total cap from being exceeded by the loan to be opened. This is related to token handling in number 159 and broader aspects of data validation in 169 and accounting issues in 171 that we discussed in the Security Pitfalls and Best Practices 201 module. Number 68 is another finding from Sigma Prime audit of synthetics ether collateral, where it was a high severity finding related to data validation and denial of service, resulting from improper storage management during opening loan accounts. When loans were opened, the associated account address got added to the accounts with open loans array, regardless of whether it was already present in that array. Additionally, it was possible for a malicious attacker to create a denial of service condition exploiting the unbounded storage array in accounts synth loans. The recommendation was to consider changing the store loan function to only push an account to the accounts with open loans array if the loan to be stored was the first one for that particular account. And 2, introduce a limit to the number of loans each account could have. This is related to the broad aspects of data validation in 169, accounting in 171, and denial of service issues in 176 that we discussed in Security Pitfalls and Best Practices 201 module. Number 69 is another finding from Sigma Prime's audit of synthetics ether collateral, where it was a medium severity finding related to configuration, in which the contract owner could arbitrarily change minting fees and interest rates. The issue fee rate and interest rate variables could both be changed by the ether collateral contract owner anytime after loans had been opened. The recommendation was to consider making the minting fee, that's issue fee rate, to be a constant that cannot be changed by the owner. This is related to the time delayed change of critical parameters in number 163, configuration issues in 165, and constant issues in 184 that we discussed in Security Pitfalls and Best Practices 201 module. Number 70 is a finding from Sigma Prime audit of Infinigold, where it was a critical severity finding related to configuration, in which there was an incorrect proxy implementation that prevented contract upgrades. The token implementation contract initialized owner, name, symbol, and decimal state variables in a constructor instead of an initialized function. Therefore, when token proxy made a delegate call to token implementation, it would not be able to access any of the state variables of the token implementation contract. Instead, the token proxy would access its local storage, which would not contain the variables set in the constructor of the token implementation contract. Hence, when a proxy call to the implementation was made, variables such as owner would be uninitialized and effectively set to their default values. Without access to the implementation state variables, the proxy contract was rendered unusable. The recommendation was 1. To set fixed constant parameters as constants, because then the proxy contract wouldn't need to initialize anything. 2. Implement a standard proxy implementation which uses an initialize function instead of a constructor, and a few other recommendations as well. This is related to OpenZeppelin's initializable in number 192 and other proxy related aspects we discussed in Solidity 201 module. The aspect of initializing state variables in proxy based upgradable contracts in number 96 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of configuration in 165 and initialization in 166 that we discussed in Security Pitfalls and Best Practices 201 module. Number 71 is another finding from Sigma Prime audit of Infinigold, where it was a high severity finding related to access control, in which the transfer from function in the token implementation contract did not verify that the sender, that's the from address, is not blacklisted. As such, it was possible for a user to allow an account to spend a certain allowance regardless of their blacklisting status. The recommendation was to use the not blacklisted address modifier on the from address besides the message sender and two addresses. This is related to the aspect of incorrect access control in number 4 of Security Pitfalls and Best Practices 101 module, and aspects of function modifiers in 141 and missing or incorrectly used modifiers in 150, 152, and broader aspects of access control in 172 that we discussed in Security Pitfalls and Best Practices 201 module. Number 72 is a finding from Sigma Prime's audit of Synthetics Unipool, where it was a critical severity finding related to ordering, in which the wrong order of operations led to exponentiation of reward per token stored value, because reward per token stored was mistakenly used in the numerator of a fraction instead of being added to the fraction. This would allow users to withdraw more funds than allocated to them, or being unable to withdraw their funds at all because of insufficient SNX balance. The recommendation was to fix the operand ordering in the expression as expected. This is related to numerical issues of 170 and accounting issues of 171 that we discussed in the Security Pitfalls and Best Practices 201 module. Number 73 is another finding from Sigma Prime's audit of Synthetics Unipool, where it was a high severity finding related to timing and ordering, in which staking before the initial notify reward amount led to disproportionate rewards. So if a user successfully staked an amount of uni tokens before the function notify reward amount was called for the first time, their initial user reward per token paid would be set to 0, and the staker would be paid out funds greater than their share of SNX rewards. The recommendation was to prevent stake from being called before notify reward amount was called for the first time. This is related to function invocation order in 145 and broader aspects of ordering in 178 and business logic issues in 191 that we discussed in Security Pitfalls and Best Practices 201 module. Number 74 is another finding from Sigma Prime's audit of Synthetics Unipool, where it was a high severity finding related to error handling in which an external call reverting would block minting. For context, the function notify reward amount would revert if block timestamp was less than period finish. But this function was called indirectly via the synthetics mint function, which meant that a revert would cause the external call to fail and thereby halt the mint process. The recommendation was to consider handling the case where the reward period had not elapsed without reverting. This is related to token handling in number 159 and the broader aspect of error reporting issues in 175 that we discussed in Security Pitfalls and Best Practices 201 module. Number 75 is another finding from Sigma Prime's audit of Synthetics Unipool, where it was a medium severity finding related to timing and denial of service, in which gap between periods led to erroneous rewards. For context, the SNX rewards were earned each period based on reward and duration as specified in the notify reward amount function. And if all stakers called get reward function, the contract would not have enough SNX balance to transfer out all the rewards, and some stakers may not receive any rewards. The recommendation was to force each period to start at the end of the previous period without any gap. This is related to function invocation timeliness in 143, token handling in 159, and the broader aspect of denial of service in 175 and timing in 176 that we discussed in Security Pitfalls and Best Practices 201 module. '76 is a finding from Sigma Prime audit of Chainlink, where it was a high severity finding related to timing and denial of service, in which malicious users could DOS or hijack requests from Chainlink contracts by replicating or front-running legitimate requests. This was made possible because requests could specify their own callbacks, which could be abused by an attacker to front-run or force the failure of legitimate requests. The recommendation was to consider restricting arbitrary callbacks by making them localized to the requester themselves. This is related to transaction order dependence aspect discussed in 21 of Security Pitfalls and Best Practices 101 and denial of service aspect of 176 and external interaction issues of 180 we discussed in Security Pitfalls and Best Practices 201 module. 77 is a finding from Open Zeppelin audit of UMA, where it was a medium severity finding related to auditing and logging, in which event emission was missing after sensitive actions. The get latest funding rate function of the funding rate applier contract did not emit relevant events after executing the sensitive actions of setting the funding rate, update time, and proposal time, and transferring the rewards. The recommendation was to consider emitting events after sensitive changes take place to facilitate tracking and notifying off-chain clients following the contract's activity. This is related to the missing events aspect discussed in 45 of Security Pitfalls and Best Practices 101 and the broader auditing logging issues of 173 along with the principle of compromise recording of 201 we discussed in Security Pitfalls and Best Practices 201 module. '78 is another finding from OpenZeppelin's audit of UMA, where it was a medium severity finding related to specification in which functions had unexpected side effects. For example, the get latest funding rate function of the funding rate applier contract might also update the funding rate and send rewards. The get price function of the optimistic Oracle contract might also settle a price request. These side effect actions were not clear in the name of functions. That is, the names sounded like getter functions, but these were also setters and therefore were not expected, which could lead to mistakes when the code is modified by new developers who weren't aware of all such project implementation details. The recommendation was to consider splitting such functions into separate getters and setters, or alternatively renaming those functions to describe all the actions that they perform. This is generally related to the programming style and naming conventions discussed in 97 of Solidity 101 module, and broader system specification, documentation and clarity issues of 136, 137 and 188, along with the principle of economy of mechanism of 197 we discussed in Security Pitfalls and Best Practices 201 module. '79 is another finding from OpenZeppelin audit of 1inch, where it was a medium severity finding related to denial of service in which Muniswap pairs could not be unpaused. For context, the Muniswap factory governance contract had a shutdown function that could be used to pause the contract and prevent any future swaps. However, there was no function to unpause the contract. There was also no way for the factory contract to redeploy a Muniswap instance for a given pair of tokens. Therefore, if a Muniswap contract were ever shut down or paused, it would not be possible for that pair of tokens to ever be traded on the Muniswap platform again unless a new factory contract was deployed. The recommendation was to consider adding unpausability for Muniswap contracts. This is related to OpenZeppelin's pausable library we discussed in 156 of Solidity 201 module, and guarded launch aspects of circuit breaker and emergency shutdown in 134 and 135, along with the broader aspects of denial of service of 176 we discussed in Security Pitfalls and Best Practices 201 module. 80 is a finding from OpenZeppelin's audit of FutureSwap v2, where it was a high severity finding related to timing and denial of service, in which attackers could prevent users from performing an instant withdrawal from the wallet contract. An attacker who observed an user's call to message processor instant withdraw in Ethereum's mempool could get the Oracle message and Oracle signature parameters from the user's transaction and then submit their own transaction to instant withdraw using the same parameters but at a higher gas price to front-run the user's transaction, but also carefully choosing the gas limit for the transaction such that the call would fail with an out of gas error at a certain point of the contract's flow. The result would be that the attacker's instant withdrawal would fail, but the user interaction number would have been successfully reserved, and as a result, the user's transaction would revert because it would be attempting to use a user interaction number that was no longer valid. The recommendation was to consider adding an access control mechanism to restrict who could submit Oracle messages on behalf of the user. This is related to the transaction order dependence aspect discussed in 21 of Security Pitfalls and Best Practices 101 module, and access control aspects of 148, 149 and 172, along with denial of service aspects of 176 that we discussed in Security Pitfalls and Best Practices 201.